Okay, so let's have another example for the slope deflection method. For example, we have this beam loaded as shown. Okay, for the span AB, we have 18 kips, 10 feet from point A. Then for span BC, we have a uniformly distributed load of 2 kips per foot. So we assume that EI is a constant and no support settlement. So we are required to compute for the moment at A, the moment at B, and the moment at C. So before we proceed to the equation of the slope deflection, so first let us compute the fixed end moments per span. So let's say we have a first span AB. Okay, so for span AB, we have a concentrated load of 18 kips. So this is A and B. So let's compute the fixed end moment at point A. So this is the fixed end moment for member AB. So what is the formula? So we have a specific formula for fixed end moments for this kind of loading. A concentrated load which is not located at the mid-span. That is the load multiplied by this distance A. So our distance is the 10 feet for A. We have the distance B squared, that will be the 15 feet for B divided by the length squared. So we have the fixed end moment for span AB, and as you can see, this is a counterclockwise moment. We assume that to be negative. So the load is 18 kips multiplied by, we have 10 times 15 squared. This is divided by 25 squared. So we have the fixed end moment for span AB. That is 18 times 10 divided by 15 squared divided by 25 squared. So we'll be having a value of negative. This is a negative 64.8 kips foot. And it's the fixed end moment for member AB or span AB. Now, if you are to compute for the fixed end moment for the span BA, this is the fixed end moment for span BA. That's equal to, you have the load. This is multiplied by A squared. That is the distance on the left of the load. Divided by B divided by the length squared. And we assume this to be clockwise. And our sign convention for clockwise is a positive moment. Okay, so this is a clockwise moment, positive moment. Okay, we have fixed end moment for span BA. So equal to, we have 18 times the distance 10, this is squared, times 15, this is divided by 25 squared. Okay, we have fixed end moment BA. We have, let's go to positive, 43.2 kips foot. Alright, so we have the fixed end moment for member BA and member AB. So let's consider the fixed end moment for member BC. So for span BC, okay, we have the fixed end moment for span BC, what is equivalent fixed end moment for this case? Uniformly distributed load. The fixed end moment on the left side is assumed to be negative. That is the uniform load, the length squared divided by 12. So we have fixed end moment for member BC is equal to negative. This is 2. We have a span of 30 feet straight. This is divided by 12. So we have the fixed end moment for member BC is equal to this is equal to negative 150 gibbs foot. So we'll be having the same magnitude for the fixed end moment on the other end, that is for span CB. Okay, but we are just assume that it is clockwise, and clockwise moments for our sign convention that will be positive. So the same magnitude, positive 150 gibbs foot. So those are our fixed end moments. So let us establish our equations for the moments. Okay, so we have, let us consider span AB. We have the moment for member AB, or our main concept for the slope-deflection method. Okay, the moment for the near point is equal to 2EI. This is divided by the length, multiplied by twice the rotation of the near point. The rotation of the near point plus the rotation of the far point minus 3 times the chord rotation plus the fixed end moment of the near point. Let us evaluate our beam. So as you can see, we have point A. Point A is a fixed support. For fixed support, okay, we have the rotation is basically equal to 0. And no support settlement, delta A is also equal to 0. So support B is a ruler, so it is prone to rotation. So we have rotation B is not equal to 0. Delta B, no settlement, that is equal to 0. Then we have again, point C is, or support C is a fixed support. So for fixed support, we have no rotation. And for this case, we don't have a support settlement. So if we have delta is equal to 0, we assume that the chord rotation is equal to delta divided by the length. That is the same as 0. So we have the value of psi will be the same as 0. So let us consider span AB. This is the moment for span AB is equal to twice of EI divided by, what is the length? We have 25 feet. This is multiplied by twice rotation of your near point. That is the first letter of the subscript. We have point A. Okay, plus we have the rotation of the far point. That is point B, the second letter. Okay, minus 3 times 0. Okay, then as you can see, we have the moment for point A. That is a counterclockwise moment. That is negative. Okay, what is that value a while ago? 18 times 10 times 15 squared over 25 squared. That is minus, we have 64.8. So we have 0 rotation at A for a fixed support. So I'll be having the moment, or the equivalent for moment AB is now equal to, what is 2 divided by 25? We have, that is 0.08 of EI, theta sub B minus 64.8. So this will be the equivalent of the moment AB. And then we consider the next span. This is for span BA. We have the moment for span BA is equal to, we have 2EI. The span is equal to 25 feet. This is multiplied by twice. What is our near point? That is point B. Twice of theta B plus theta A minus 3 times psi is 0. Then your fixed end moment that is on the right, that will be positive. plus, I think, what is that value a while ago? That is 18 times 10 squared times 15 over 25 squared. That is plus 43.2. So we have, again, there's no rotation for a fixed support. So we have theta A is 0. So we're having the equivalent of the moment for span BA is equal to, so this is 2 times 2. That is 4 divided by 25. We have 0. This is 0.16 of EI. Theta should be then plus 43.2. So this will be the equivalent for moment BA. Let us consider the next span, the span CB and span CB and span BC. We proceed to span BC. So from our general equation, we have the moment on the near point is equal to this is 2EI divided by the length. This is multiplied by twice of the rotation of the near point. Plus the rotation of the far point minus 3 times the chord rotation psi. Plus the fixed end moment of the near point. So for example, we have for span BC, that is the same as the moment for span BC is equal to 2EI. This is divided by the length. Twice our near point is point B, twice of rotation of point B. Plus the rotation of our far point is point C. That is theta C minus 3 times the psi. Plus the fixed end moment for member BC. This will be our equation. Now we substitute. We have the moment for span BC is equal to twice of EI. This is divided by the length of span BC. We have 30 feet. This is multiplied by twice of theta sub B. Plus we have theta C is 0. So 0 rotation for a fixed support. Then we don't have a chord rotation that is also 0. Then I saw BC, that is the support on the left, so it should be negative 150. The fixed end moment BC. We have the moment for span BC is the same as this 4 over 30 is equal to 0.133 of EI. Theta sub B minus 150. So this will be the equivalent of moment BC. Then we for the next span, let's say span CB. That is the moment for span CB is equal to 2EI. This is divided by the length. This is multiplied by twice your near point theta C plus the rotation of your far point, that is point B, minus 3 times the psi, plus the fixed end moment. This is for span CB. We substitute. We have the moment for member CB is equal to twice of EI. This is divided by 30. Multiplied by theta C again. We don't have a rotation for a fixed support. This is 0. No chord rotation, 0. So we have this is theta sub B. Then that is support on the right. That will be positive 150. So we'll be having the moment for span CB is equal to that is 2 over 30 is equal to 0.067 EI. Theta sub B, then plus 150. And this will be the equivalent of moment CB. So we are to proceed with the equation or with the equations. Equivalent of moment AB, equivalent of moment BA, and equivalent of moment BC and CB. We have the equivalence of the moments per span. The equivalent of moment AB, BA, and BC. So we can use this at joint B. Okay, the moment for member BA and member BC. Okay, the summation of moment about joint B should be equal to 0. So again, we assume one moment is acting counterclockwise, the other is one is counterclockwise, the other is clockwise. That is the same as the summation moments about joint B. We have that is the moment for member BA plus the moment for member BC should be equal to 0. So we have is the equivalent of moment BA. That is 0.16 of EI. This is theta sub B. Okay, plus 43.2. So that will be that is the equivalent of the moment for member BA. Then we have the moment for member BC. That is we have 0.133 EI theta sub B. Okay, less 150. And the summation of moment about joint B should be equal to 0. So let us compute for the equivalent of at EI theta sub B. We have the equivalent of EI theta sub B is equal to 364.505. 364.505. This is in terms of kips foot squared. So we can now compute. For the moment per point, the moment at A, the moment at B, and the moment at C. Okay, so since we have this value, okay, we may compute for the moment at AB, for span AB. Okay, the moment for span AB is equal to, we have 0.08. Okay, the equivalent of EI theta sub B, that is equal to, we have 364.505 minus 64.8. So we have the moment for span AB, this is the same as the moment at A. Equal to we have 35. This is equal to negative 35.64 kips foot. Is the moment AB or the same as the moment at A? We'll be having the moment for span BA. Alright, we have the equation that is 0.16 of EI 364.505 minus BA, that is plus 43.2. So we have the moment for span BA we have 101, this is positive, 101.521. This is kips foot. Moment BA. The next, we have the moment for span BC. We have moment for span BC is equal to 0.133 of EI 364.505. This is minus 150. So we have the moment for span BC is equal to let's equal to negative. We have negative 101.521 kips foot. So as you can see, we have the moments for BA and BC are numerically equal but opposite in sign. Then lastly, we have the moment CB. We have moment CB is equal to, we have 0.067. What is the value of EI? 364.505. Then plus, this is plus 150. So this is the moment for span CB, or the same as the moment at C. That is 0.067 364.505 plus 150. So we'll be having a moment of 100. This is positive 174.422 kips put. That is the same as the moment at C. So we have the moment at for span AB, or it's the same as the moment at A, negative 35.64. And the moment at C is positive 174.422. But if we are to analyze what is the actual moment at B, so let's say this is the moment B. What is the moment for span AB? If we are to cut that section, we have a positive moment, that is moment BA. That is, we have moment BA equal to 101.521. That is a clockwise moment. So supposedly at B, we have a negative 101.521. On the other side, we have that is moment BC. That is, for our moment BC is equal to negative 101.521, and that is counterclockwise. So to be equilibrium, if we are to transfer that moment on this side for B, this is positive 101.521. As you can see, we have a negative bending moment about joint B. So again, the actual moment at joint B, that is a negative bending moment. So that is negative 101.521 keeps foot. A negative bending moment at joint B. You can check this one if you are to draw the shear and moment diagram of the beam. So therefore, our answers, moment at A is negative 35.64. Moment at B is negative 101.521. Then, moment at C, 174.422 keeps foot. This is our example for the slope deflection method.